we're going to master graphing this function like a pro for calculus students. And at the end, I'm going to show you a special surprise in the graphing process. So let's look at this function y equals x plus 1 over x. The first step is always to find the domain. Okay, so we'll keep it really simple. You just want to find the domain of the function. Okay, so I'm going to write it as step 1 is find the domain. Now, how do we find the domain of a function? The main thing is just to check that we're not taking the square root of a negative number, not dividing by 0, not taking the logarithm of a number that is 0 or negative. Okay, so those are the basic principles. There's more to it, but those are the principles. So here we just want to avoid dividing by 0 because we have a 1 over x. So the domain is just going to be this union of open intervals, minus infinity 0, union 0 infinity. So just as a review, this is all numbers that are negative and this is all numbers that are positive. And the parenthesis indicates we're not including the endpoint. So we're not including 0 in this expression. We're taking the combination of these two. Now once we've found the domain, we've got some preliminary idea of how to graph the function. The next step can vary. It's either finding the x and y intercepts, or it's going to be finding the derivative to understand where the function's increasing and decreasing. So I'm going to do the derivative first. Okay, domain is always the first step, but you can then do the other steps in whatever order you like, generally speaking. So I'm going to find the derivative. So if we have the function y, then y prime, so one way of writing this is x plus x inverse. So you can clearly see the power rule for differentiation. Y prime is going to be 1, and then for the power rule, your minus 1 is going to come out on top, and you're going to get an x to the minus 2. Your exponent's going to decrease. So we can write this as 1 minus 1 over x squared. Okay, so that's the derivative of f. Now we need to figure out when this is positive or negative, and one step is to first figure out when this is 0. Okay, so that's where the function has critical points. So when's the derivative going to be 0? So we're just going to be looking at, we've seen y prime is equal to 1 minus 1 over x squared. Set that equal to 0. So that's going to equal to 0 if and only if 1 is equal to 1 over x squared, which is the same as saying that x squared is equal to 1 if we multiply both sides by x squared, and that's the same as saying x is equal to plus or minus 1. So those are the critical points. But in order to figure out the nature of those critical points, whether they are local maxima or local minima, we need to either find the second derivative, or we just need to find out where the derivative is positive or negative and see what kind of sign change we have. So I'll go over that point too. But how do we do that? So a nice way I like to do that is in understanding the sign of y prime, right? Because we know that y prime is equal to 1 minus 1 over x squared. Understanding the sign, you can just multiply both sides by x squared. Okay, so if we want to solve for the inequality, so I'm going to write this out here, you want to solve for this being greater than 0, we just multiply both sides by x squared, which is always a positive number. So when x is non-zero, when you are looking at the domain of the function when x is non-zero, x squared is always going to be positive, so we're not going to change the sign of the inequality. So multiplying both sides by x squared, this is the same as saying x squared minus 1 is greater than 0. So we're trying to solve for when the derivative is positive. So we just keep going. So this happens precisely when x squared is greater than 1. And now we can take the square root on both sides. Okay, so square roots preserve inequalities. Okay, so we can do that on both sides because both numbers are positive. And we're just saying when the square root of x squared is greater than 1. That's when the derivative is positive. So here's a cool rule that the square root of x squared is actually just going to equal to the absolute value of x. So think about it. If x is negative, its square is positive, its square root is positive. So you get a positive number, it's going to be the absolute value of x. Okay, so when x is positive, you just get back x. So this is the absolute value of x. So that inequality saying that square root of x squared is greater than 1 is just the same as saying that the absolute value of x is greater than 1. And we can solve that inequality. When is the absolute value of x greater than 1? That's just a union of two intervals. Okay, so the interval is going to be minus infinity minus 1. Absolute value of x is the distance from x to 0. So the distance from x to 0 is greater than 1 when x is either to the left of negative 1 on the number line, or when x is to the right of 1 on the number line. So you have a union of these two open intervals. You're just taking all numbers less than minus 1 and all numbers greater than 1. And that's when the derivative is going to be positive. And we know that the derivative is going to be negative on the opposite. Okay, so when you have the interval minus 1, 1, that's when the absolute value of x is less than 1. That's going to be when the derivative is going to be negative. So you have y prime less than 0 there. Okay, so we've got these two intervals, and now we know when f is increasing or decreasing. So let's neatly summarize our information here. All right, so I'm going to draw a little sign chart here, which is just to summarize everything. On the interval minus infinity minus 1, we saw y prime was positive. Then on the interval minus 1, 1, we saw that y prime was negative. And then on the interval 1 infinity, we saw that y prime was going to again be positive. Okay, so that's our sign chart. And if you're enjoying the content so far, please don't forget to smash that like button and subscribe. Makes a huge difference, helps you keep notified of constant math content across all topics and levels. And you're going to love the rest of this video. We're going to now graph the function, and I'm going to show you a special surprise. So you observe that at minus 1, your derivative is going to change sign from positive to negative. So your function is going to go from increasing to decreasing. So your minus 1 is going to be a local max. Okay, so we can write that down here. Minus 1 is going to be a local max. And then at 1, you're going to see that the derivative, the sign is going to change from negative to positive. So your function is going to change from decreasing to increasing. Okay, so it's going to look something like this. So you're going to have a local min. Okay, so at plus 1, you're going to have a local min. And these are the natures of the two critical points. Now we could have also calculated the second derivative, and we will do that. But you see that minus 1 and plus 1, you can find out what they are just by looking at the sign change of the derivative. And anyway, knowing the derivative is going to be pretty important. So let's now work out how the graph is going to be. Okay, so I'm going to just erase this. So now we're at the fun point. Okay, we're just trying to figure out the graph. And you'll see there's one more crucial information we need to work out. Okay, so before we actually can finalize graphing our function, we need to understand what is happening at the endpoints of the domain. Okay, this is going to be very crucial in all graphing problems. The domain of our function was minus infinity 0 union 0 infinity. And so we need to figure out what happens when you approach negative infinity, when you approach positive infinity. Then we're going to connect the dots. Okay, so we know that 0 is not in the domain, so we need to figure out what the function does here. What the function does is it approaches 0 from either the left or the right, because you've got two different intervals here. And then what the function does as you approach infinity. And then we're going to connect the dots, okay, using our sign chart for our derivative. So there are going to be a few limits we're going to be looking at. Okay, so the limits we're going to be looking at are limit x goes to minus infinity of x plus 1 over x. So what's that going to be? So the way we just do this is that x is going to approach minus infinity. X here is going to approach minus infinity, which means 1 over that is going to be very close to 0. So you're going to have minus infinity plus something very close to 0. It's just going to be minus infinity. Okay, so we're just going to get minus infinity here. It's a pretty kind of straightforward limit to work out. You know, you just have to get a sense of what each term is doing. We don't have any 0 over 0 or anything messy like that. Then the next thing we want to look at is limit x goes to plus infinity of x plus 1 over x. And the idea is very similar. As x goes to plus infinity, 1 over x goes to 0, because you're dividing by something really large, 1 over that. And so this quantity is going to go to something that's getting very large plus something that's very close to 0. So it's also going to be plus infinity rather than minus infinity. Okay, so we're getting somewhere here. Now we need to figure out what happens at 0. And it's going to be very, very similar and very symmetric. Now before we get to the 0 limits, I'll mention to you a special surprise, which is oblique asymptotes. This function is actually something where we can understand that, and I'll explain how it works. The idea is that as your x goes to negative infinity, x plus 1 over x is just going to be x plus a number that is going to be very close to 0 but negative. So it's going to be your y value is going to be something that is very, very slightly less than x as x approaches negative infinity. As x approaches positive infinity, your 1 over x is going to become very close to 0, but it's going to be positive. So your y value is going to be something that's very slightly more than x. So this line y equals x plays a special role, and it's what we call an oblique asymptote. And what that means is that, let's just draw this line. So this is our line y equals to x. What's going to happen with this line is, as I just said, as x approaches negative infinity, your graph is going to be slightly below this line y equals x. Okay, so it's going to approach the line, it's going to get closer and closer to the line but slightly below, and we know that its limit is going to be negative infinity, so we can sort of see this part of the graph. I'm not going to keep drawing, I'll connect the dots once I get to the behavior at 0, but then we also know that when on the similar side, when we look at x goes to positive infinity, again your graph is going to approach the line y equals x, going to be slightly above that. Now that's going to give us a sense of what the graph is doing at infinity and minus infinity. Now let's figure out what happens at 0. Alright, so as x approaches 0, we're going to look at limit x goes to 0 from the left and from the right of x plus 1 over x. So as x approaches 0 from the left, I've put a negative sign there. we're going to basically see that x plus 1 over x is going to approach 0, 1 over x is going to approach negative infinity because it's 1 over a number that's negative but very close to 0. So it's going to approach negative infinity, x is approaching 0, so this is going to be negative infinity. So we're kind of getting a sense now, we can keep drawing, okay? So this is our graph, it's going to kind of go like that. Okay, so I'm just sort of going to connect the dots. We're going to then see the sign change. Remember, it's increasing and then decreasing. We saw that at -1, you have a local max. So you're going to get the sense of that. In fact, let's actually do that right now. Let's just see that at -1, you're going to have a local max and your function is going to change from increasing to decreasing. And this is where I'm just going to label our -1 on the graph. We know that at x equals -1, our function is -1 plus 1 over -1, which is -2. Okay, so I'm just going to put our -2 here, and then we're going to just graph our function like this, and we're going to get something like that. And here, you just put a label, nice little label there, you'll just put a local max, so I'm just going to write this as follows, local max at the point -1, comma, -2. Okay, so that's our function. Now at this point, we can also do it in two ways. I'm going to show you the slightly slower way and then the super tricky, beautiful way. Okay, so I'm just going to do the same thing for x positive. I'm just going to say limit x goes to 0 from the right hand side is just going to be of x plus 1 over x. It's just going to equal to, well, x approaches 0, 1 over x is going to approach infinity because x is positive but getting close to 0. So this is going to equal to positive infinity. And so you're going to get a graph that looks like this. And again, you're going to have, this time it's going to be your local min, is when you have a sign change, your derivative is going to go from negative to positive. So it's going to be decreasing and then increasing. And at 1, that's going to be where your local min is. You can sort of say this is going to be plus 1. You notice that your value of your function is 2, 1 plus 1 over 1, which is 2. And you're going to get our function that's going to look like this. Now here's where I want to mention something to you, which is very, very crucial and a quick way of understanding these kinds of problems, is our original function is actually what's called an odd function. If you call this function f of x equals to x plus 1 over x, you notice there's a symmetry when you find f of minus x. F of minus x is just going to equal to minus x minus 1 over x, which is minus of x plus 1 over x, which is just minus f of x. So f of minus x is minus f of x, that's what we call an odd function, which means that our function is literally going to be reflected across the origin. Our graph of our function is going to be reflected across the origin, which we see here. So we could have just found out what happens for x negative and just replicated that for x positive. But hopefully you kind of sort of see it. It helps to kind of see it in a couple of ways to make sure you understand the principle. But there you have the graph, and you have an oblique asymptote at y equals x. And if you want to find the concavity, you can do that too. So I'll just finish off with that. The concavity is kind of self-explanatory, but let's just go for it. So y prime is just going to equal to, as we found earlier, it was 1 minus 1 over x squared. Differentiate again and find y double prime. You're just going to get minus of 2 over x cubed. Okay, so you're going to get minus of 2 over x cubed. And now if you just notice that when x is negative, this is going to be a negative number. And when x is positive, this is going to be a positive number. So you see that it's going to be concave down for x negative and concave up for x positive. That's pretty straightforward. That's what we see in the graph. So there's nothing really there to it. We've just been able to sketch the graph pretty easily. If you're enjoying my content, as I said, like and subscribe, and please consider supporting the channel on Patreon or on a YouTube channel membership by clicking the join button, which you can do on a desktop browser or on Patreon, links in the description. Means the world, and a huge thank you so much to Alex, Nathan, and Trang for their ongoing support. Now I have 2 fun videos for you. The first is another graphing video using calculus principles, but this time the limits are going to be a lot more complicated. The limits at the endpoints, and there are going to be some other subtleties too. It's going to involve logarithms. You can check that video out. It's going to pop up on the screen here. And for another fun video, just to kind of refresh different kinds of graphing without using calculus, okay, just to get a stronger sense of how to graph functions, here's a beautiful tutorial on how to graph rational functions, kind of for pre-calculus students, but there's a lot of lovely kind of introduction to lots of fundamental ideas.